One of the assumptions we've been talking about ever since we started talking about population genetics is that for a lot of the calculations you have to assume that a population mates randomly. In the real world, random mating basically never happens. Here's a huge population of flowers. This is the California poppy. And you can see they're spread over this tremendously large landscape. Are the odds really equal that, say, this individual right here is just as likely to mate with this individual way up here as it is to mate with this one that is a few inches away? No. Individuals are usually going to mate with individuals that are close by. That's an obvious truth. And if allele frequencies are different down here than they are up here, what that means is that individuals are going to be doing what's called positive assortative mating. Positive assortative mating just means like mates with like. Negative assortative mating is when individuals are unusually likely to mate with individuals that have a different genotype. So that's opposites attract. So usually in nature what you see genetically is like mates with like, but sometimes you do see opposites attract. The result of this is probably going to be pretty obvious. If the A1 allele is very common in this population down here in the valley, and the A2 allele is more common up here in the hills, and everybody is mating with nearby individuals, you're not going to see as many A1, A2 heterozygotes in the next generation as you would have if this population really had been mating randomly. Okay? So the two alleles aren't independent from one another when you have positive assortative mating. And from now on, I'm just going to talk about positive assortative mating because that's by far more common. Okay, you should be really familiar with this diagram and with the math involved. Where things get wonky is at this step. Because if you have positive assortative mating, like mates with like, then the fact that this is an A1 allele here tells you something about which allele is likely to be in the sperm, which allele is likely to be donated by dad. If you've got like mating with like, if you've got, say, an unusually large number of A1 individuals mating with A1 individuals, then the probability of getting a second A1 allele here is not the same probability as if you were reaching in the population and pulling an allele out of a bag. And a female that has an A1 allele to put into her egg cell is unusually likely to be mating with a male who also has an A1 allele to put into his sperm. So if this happens with probability p, the frequency of the A1 allele, then that means dad is probably going to donate an A1 allele with a frequency that's greater than p. Similarly, he's going to have to, if this is true, he's going to have to donate an A2 allele with a frequency that is less than q. And you can see it's going to be the same thing down here. What does this mean over in this column? Well, it means that the probability of getting an A1 homozygote is larger than p squared. It means that the probability of getting an A2 homozygote is greater than q squared. But these are both going to be less than pq and less than qp, and so the frequency of heterozygotes is going to be less than 2pq.